Observations made with the Hubble Space Telescope over the last 3 decades have shown that all galaxies contain black holes in their center. Larger black holes are found in larger galaxies. Black holes are prisons for matter where nothing, not even light, can escape. Anyone pulled into a black hole would experience a painful demise, according to Stephen Hawking, who popularized the concept in his book, A Brief History of Time. Astronomers were first alerted to the existence of this black hole when it tore apart and swallowed a star that drifted too close to it. The star was destroyed by an intermediate mass black hole that is 1 million light-years away in a phenomenon known as a tidal disruption event, or TDE. When the TDE unleashed a radiation flare that was more intense than the sum of all the stars in its dwarf galaxy home, it became visible. The interaction between galaxies and the black holes that reside inside of them may be better understood because of this TDE. Additionally, it offers astronomers a second intermediate black hole to research. Astronomers first saw the TDE flare as the black hole started to eat the star using the Young Supernova Experiment, an astronomical survey that finds transient cosmic phenomena like supernova explosions. It was only via careful study of this first instant of devastation that astronomers were able to calculate the black hole's mass, which they discovered to be somewhere between 100,000 to 1 million times that of the Sun. This is the first time that TDEs have been shown to be effective in determining the masses of smaller mid-sized intermediate mass black holes. TDEs had previously been used to determine the mass of supermassive black holes. Capturing this moderate-sized black hole as it swallowed a star provided a unique chance to see details that would otherwise have been hidden. Furthermore, we may learn more about this elusive class of middleweight black holes, which may make up the bulk of the black holes in the cores of galaxies by studying the flare's physical characteristics. They are much more massive than stellar mass black holes, but considerably less than the supermassive black holes that reside at the center of most galaxies, including the Milky Way. The mass range of this mid-sized class of black holes is between 100 and 100,000 times that of the Sun. Supermassive black holes, which may have masses that are millions or even billions of times greater than the Sun, have long been thought to have grown to these enormous masses as the consequence of the merging of intermediate mass black holes. According to one idea, there were many dwarf galaxies with intermediate black holes in the early universe, which may have contributed to this development. The intermediate black holes within these dwarf galaxies cannibalized one another, rising in mass when they joined or were sucked up by bigger galaxies. The supermassive black hole titans that are at the center of the majority of galaxies today are the result of this chain reaction of mergers that become bigger and bigger over time. We can assess if our ideas of the development of supermassive black holes are accurate if we can comprehend the population of intermediate mass black holes that already exist, including their number and location. There is still one question. Do all dwarf galaxies possess a central black hole of intermediate mass? This question is challenging to address since black holes are essentially undetectable unless they are consuming nearby gas and dust, or if they are tearing apart stars in TDEs because they confine light behind an outer limit called the event horizon. Other techniques, such as examining the gravitational pull of the stars that circle them, may be used by astronomers to deduce the existence of black holes. However, these detection techniques are not yet sensitive enough to be used to identify far-off black holes at the cores of dwarf galaxies. Few intermediate mass black holes have so far been located in dwarf galaxies. TDE flares might thus be a key instrument in resolving the controversy over the development of supermassive black holes by identifying and monitoring mid-sized black holes. In a recent study, scientists saw the demise of a star by a supermassive black hole, demonstrating how these cosmic giants eat the matter from things that approach them too closely. According to the findings, a significant portion of this matter is blasted away from the black hole, rather than being eaten by it. The gruesome event, which occurred 215 million light-years from Earth, was first seen in October 2019. It is the outcome of a sun-like star being destroyed by a black hole that is more than 1 million times as massive as the star ever was. This TDE took place in a spiral galaxy in the Eridanus constellation. It was the first such event to be bright enough in visible light to enable astronomers to examine the details of what happens to star material after it is destroyed. Researchers discovered that most of this star debris was propelled out from the black hole at velocities as high as 22 million miles per hour by looking at the polarization of light from the event. These new polarized light studies show that the gas cloud produced by this explosion, known as AT2019 QIZ, is spherically symmetrical. The average distance between the Earth and the Sun is 200 times wider than this gas cloud. This indicates that it has a radius 100 times greater than the orbit of our planet, and that its outer edge is 930 million miles from the primary black hole. A supermassive black hole's ability to devour a star with its powerful tidal forces is one of the wildest things it can accomplish. One of the few ways astronomers may confirm the presence of supermassive black holes at the cores of galaxies and quantify their characteristics is via star tidal disruption events. However, since numerically calculating such occurrences has such a high processing cost, astronomers still don't fully comprehend the intricate processes that follow a tidal disturbance. The new discoveries could help to explain why additional TDEs are not seen for high-energy emitters like X-rays. These emissions are caused by the star's material being drawn into the black hole's narrow disk. When this material is heated in the disk, high-energy emissions are produced, which also happen when it falls into the black hole. These gas clouds, which are the result of strong winds, block off these pollutants. The intriguing aspect of this situation is that a sizable portion of the star's material that is spiraling inward gets blasted away from the black hole rather than falling into it. The findings seem to refute the widely held belief among astronomers that a highly uneven accretion disk develops when a star is obliterated by a black hole. Such a disk would exhibit intense polarization of the light, which is not seen in this TDE. The light from this event in November 2019 was only marginally polarized, according to the second set of observations. This result revealed that the gas cloud of material expelled by the black hole had thinned enough to expose the asymmetrical gas structure. The accretion disk is hot enough to emit the majority of its light in X-rays, but this light must travel through the cloud, where it undergoes several scatterings, absorptions, and remissions before leaving. All the way down to ultraviolet and optical energies, the light loses part of its photon energy through each of these processes. The polarization state of the photon is then determined by the last scatter. Therefore, we may determine the shape of the surface where the ultimate scatter occurs by measuring polarization. Polarization studies are very difficult, and very few persons are proficient enough in the method to use this worldwide. Therefore, these tidal disruption occurrences are new. Thanks for watching. Don't forget to like the video and subscribe to the channel. Until next time.